Molecular orbital theory. So unlike valence bond theory, where we're looking at orbitals that are specifically on an atom, and we're looking at overlap of two orbitals, here we're looking at orbitals calculated for the entire molecule instead of just for one of the atoms. So solving the Schrodinger equation exactly, even for a simple molecule, is just flat out impossible. And so what they do is they take a trial function, an educated guess, we think, well, this might be close, and they put that into a very powerful computer, and they see what it comes out with. And so then they tweak the function a little bit until they get the lowest energy that they can. So this is how we approximate molecular orbitals. Of course, we can never do better than nature at minimizing the energy of these orbitals, but we try. So what we refer to as an LCAO, linear combination of atomic orbitals, is where we take atomic orbitals and put them together. So it's a weighted linear sum of the valence atomic orbitals of the atoms in a molecule. This is the simplest of the trial functions that works reasonably well. So it combines the valence atomic orbitals of all the atoms in the molecule. That's a big distinction with valence bond theory, which looks at only orbitals from individual atoms. So many of these orbitals are delocalized over the entire molecule, whereas the hybrid orbitals we were looking at last week are localized on a single atom. So any questions about the difference between these two theories? So let's look at the simplest molecule possible, H2. So we're going to see conservation of orbitals again, where if you start with two orbitals, you end up with two orbitals. So one of the molecular orbitals is the equally weighted sum of the 1s orbital from each of the atoms. So here's the 1s orbital from one hydrogen atom, the 1s orbital from the other hydrogen atom. So you add those together, and you get a bonding orbital. The bonding orbital is lower in energy than the atomic orbitals. Remember, a bond won't form between the two hydrogen atoms unless doing that lowers the energy. So here's our bonding orbital. This is called a sigma orbital because of its shape, as in valence bond theory, where we looked at the names of the bonds. Sigma was symmetrical, and this one is symmetrical. So if you look from this nucleus down the axis to the other nucleus, it would be spherical, symmetrical. So that's a bonding orbital. So sigma 1s, sigma because of its shape, 1s because it's the combination of 1s orbitals. We can also look at combining those same two orbitals when they are in opposite phases. So this is a lot like subtracting. So we take the two orbitals, we add them together, we take the two orbitals, we subtract them. Or you can think of it in terms of interference. Remember, we looked at waves, and waves can constructively interfere, and they can also destructively interfere. So the bonding orbital is constructive interference between these two orbitals. And remember, an orbital is a lot like a standing wave. And this would be the destructive interference. So destructive interference would cause the energy of this orbital to be higher. It's going to have a node between the two atoms, and we call this an anti-bonding orbital, because electrons going in here raise the energy of the molecule, which is not going to facilitate bonding. So this is also sigma, because if you look from one nucleus to the other along this axis, this bond is, or this orbital is symmetrical. But we call this sigma star 1s, and the asterisk there means that it's an anti-bonding orbital. Any questions? So when we put these two atoms together and form molecular orbitals, we're going to form one through constructive interference. That's going to be the bonding orbital, and we form one through destructive interference. This is going to be higher in energy. This will be lower in energy than the original orbitals. The anti-bonding orbital has a node, or pointer, a node between, and so there's a space in the middle there where the electron never, well, pretty much never is, right? And so that's not going to facilitate bonding. The bonding orbital has the largest electron density between the two atoms, and that's going to act as a bond and hold the two atoms together. So we take our orbital diagrams where we had the little boxes and the arrows, and we can use that same idea to visualize these molecular orbitals. So energy is always increasing as we go up. So here's the 1s orbital from this hydrogen atom, the 1s orbital from this hydrogen atom. And when we combine these to make molecular orbitals, we're combining two atomic orbitals. We're going to have two molecular orbitals. One's going to be lower in energy, this guy down here. One's going to be higher in energy, and we label them sigma star 1s and sigma 1s. Each of these hydrogen atoms has one electron, and so after we determine what the molecular orbitals are, then we fill in those orbitals using the same pattern we've been using, where you fill in the lowest orbitals first. If there are degenerate orbitals, you fill them half full with one electron first before you pair them up. So this is a molecular orbital diagram for hydrogen. We talk about something called bond order, and that helps us to predict whether a bond will form or not. A bond order for a diatomic molecule is the number of electrons in bonding molecular orbitals minus the number in anti-bonding molecular orbitals divided by 2. So this is the calculation of the bond order for hydrogen. Let's go back and look at this diagram. How many electrons are in the bonding orbital? 2. And how many are in the anti-bonding orbital? 0. So we take the number electrons in bonding orbitals minus those in the anti-bonding, and then we divide by 2. So it's sort of an average. So the bond order for hydrogen is 1. If that bond order is positive, a chemical bond will form, because that means that there are more electrons in the bonding than in the anti-bonding. And so overall it'll have lower energy. A higher bond order indicates a stronger bond. And if you have the bond order being 0 or negative, it means that a bond will not form. So we can use bond order to predict whether bonds will form. So let's look at He2. So 2 helium atoms, and see what happens when they try to bond. So here we have this helium atom has 2 electrons in its 1s orbital. This helium atom has 2 electrons in its 1s orbital. The combination of these 2 1s orbitals gives us a bonding orbital and an anti-bonding orbital. We have a total of 4 electrons, so we put them in. We fill up this one first, 1, 2, and then we go up to this one, 3, 4. And then to calculate the bond order, take the number of electrons in bonding orbitals, 2, minus the number in anti-bonding orbitals, 2, and divide it by 2, and we come up with 0. So bond order equals 0. What does that tell us about this bond? It doesn't exist. It's not going to happen. And it doesn't. Helium does not form a diatomic molecule. Any questions? What if we try to make an He2 plus ion? Well, He2 plus would be He2, which had 4 electrons, that's lost 1 electron, so only 3 electrons. The molecular orbital diagram is essentially going to be the same, but now we have to take that electron from somebody, so we'll just pick one to remove an electron from. So we've got an He plus ion and an He atom. Same arrangement of molecular orbitals, but 3 electrons now. So 2 in the bonding, 1 in the anti-bonding. So when we calculate bond order, we've got 2 in the bonding and 1 in anti-bonding, and that's divided by 2, that's 1/2. 1/2 is a positive number. It's not very large, but it's positive. And so molecular orbital theory predicts that He2 plus exists, and it does. Now it's not common, but you can make it. So, a summary. We are approximating molecular orbitals as linear combinations of atomic orbitals. We're taking these 2 wave functions and just adding them together, or, we're adding them either in phase or out of phase. However many atomic orbitals we start with, and we're only looking at the valence orbitals, that's the number of molecular orbitals that we'll end up with. When we combine atomic orbitals, one of those molecular orbitals that's formed will be lower in energy, a bonding orbital, and another is higher, an anti-bonding. So you take 2 orbitals, no matter what kind they are, and you add them together, you're going to get 2 orbitals. One will be lower in energy, one will be higher in energy. When we put electrons in those molecular orbitals, we fill the lowest energy ones first with up to 2 spin-paired electrons, and we follow Hund's rule. If there are 3 or more, if there's more than one, let's start that over. If you have degenerate orbitals, orbitals with the same energy, you'll fill them with 1 electron first before you pair them up. And stable bonds require a positive bond order, meaning we've got more electrons in the bonding orbitals. When we have more electrons in bonding orbitals than anti-bonding orbitals, then that formation of molecular orbitals causes a lowering of energy, and that's what happens when a bond forms. Okay, let's use molecular orbital theory to predict the bond order in He2 plus. Is that bond stronger or weaker than the H2 bond? Okay, so what we're going to do here is we're going to start with the 2 atoms. So we've got He2 plus. So we'll put a hydrogen over here and a hydrogen over here, but one of them is missing an electron, right? So we'll make this one H plus. And then we look at the combination of these 2 orbitals, and they're going to make 1 bonding orbital and 1 anti-bonding orbital. And we often draw these dashed lines to show what original orbitals those came from. So this is called sigma star 1s. This is called sigma 1s. Energy is increasing as we go up the screen. So how many electrons does a hydrogen atom have? 1. So that hydrogen atom has 1 electron in its 1s orbital. This hydrogen ion has no electrons, right? So we have 1 electron to put into the molecular orbitals in the middle, so that's going to go down here. And then we need to predict the bond order. So bond order is number of electrons in bonding orbitals. How many? 1. Minus the number of electrons in anti-bonding orbitals. 0. Divided by 2. So that's a bond order of 1/2. The bond order for H2 was 1. is this bond stronger or weaker than an H2 bond? It's weaker. Because this is a smaller number. H2 had a bond order of 1. The larger the bond order, the stronger the bond. Any questions? Yeah?
What happens when you have more than 4 electrons to distribute?
So what happens when you have more than 4 electrons? If you have more than 4 electrons, you're going to have more than a 1s orbital on each atom, because each orbital brings at most 2 electrons. So there will always be room for all the electrons. So we did the first row on the periodic table. Let's go to the second row, period 2. Here, we're looking at homonuclear diatomic molecules. Homonuclear means the 2 atoms are the same element. Diatomic, there's just 2 atoms. So Li 2+. Now we're looking at a 2s orbital from each lithium atom, because that's the valence orbital. We're going to ignore the 1s. We don't look at those. So here is an electron diagram for the valence orbital on a lithium atom. Here's the other lithium atom. 2s orbitals are going to combine into molecular orbitals in the same way that 1s orbitals do. So we're going to get a sigma, a bonding orbital, we'll call that sigma 2s, and an antibonding orbital, sigma star 2s. We have 2 electrons, we're going to put them into the lowest energy orbital first. They're going to pair up, and then we're done because there were only 2 electrons. So we can look at the bond order of this. It's the number of electrons in bonding orbitals, 2, minus the number in the antibonding, 0, divided by 2. This has a bond order of 1. Positive bond order says this should exist, and it does. It's not common, but it does exist in the gas phase. Any questions? Yeah?
Can you have a negative number?
Yes, you can have a negative number. There can be situations, not with the 1s, not with s orbitals, but with p orbitals, where you have more electrons in antibonding orbitals than you do in bonding orbitals. Yeah, so you can have negative numbers.
Does that suggest that the bond doesn't exist?
The bond would not form. Yeah, because doing so would cause the energy of the molecule to rise. And that's like, looking at a bowling ball at the bottom of a hill and it just spontaneously rolls up the hill. That doesn't happen, right? We're like, no, of course that doesn't happen. So a bond order that's negative, chemist says, well, of course that doesn't happen. That's as crazy as a bowling ball rolling up the hill by itself.
So how would that happen if we're filling in the bonding first?
That can't happen with s orbitals. But we'll see that it can happen with p orbitals. Good question. Whoops, where am I having issues? Okay, let's look at the next element, Be2. So beryllium pointer? No pointer. Beryllium has 2 valence electrons. Those are in the 2s orbital. Sorry about the screen. Those 2s orbitals are going to form the same 2 molecular orbitals. But putting 4 electrons in, we put 2 in the bonding and then 2 in the antibonding. And when we calculate the bond order, it's 2 minus 2 is 0, divided by 2, so the bond order is 0. So we predict that Be2 does not exist. Yes?
What if it's Be2 2+? Are you going to
Be2 2+ would be different. Yes. Be2 2+ would not have 4 electrons, it would have 2. And so you would remove the 2 electrons in the antibonding orbitals, and that would have a bond order of 1 and would be predicted to exist. Okay, so looking at boron, now boron has an electron in a 2p orbital. valence electron. So now we have to look at how do the p orbitals combine. Well, remember the p orbitals are oriented along the three-dimensional axes x, y, and z. And so if we take the two orbitals that are aligned on the x-axis, and we combine those, we can have constructive interference and destructive interference. So we can get a bonding orbital and an anti-bonding orbital. This one is sigma 2p, sigma star 2p. And if you imagine looking down the axis, it would be symmetrical, right? So that's why it's a sigma. This is a lot like a sigma bond in valence bond theory, but we're looking at making new orbitals. What do the other two do? Well, there's p orbitals along the y-axis, and so when these overlap, positive interference, negative interference, we get a bonding orbital and an anti-bonding orbital. But these are not symmetrical along the axis, and so these are the pi orbitals. So pi 2p and pi star 2p. This has this big chasm. This anti-bonding has the node in the middle where there's no electron density between the atoms. So it fights against bonding. And then the third pair of orbitals is along the z-axis, and combining those, we get the same shapes as we did for the y, but they're oriented differently in space. So here's our bonding orbital and our anti-bonding orbital. Any questions? So what are the relative energies of these new molecular orbitals from the p orbitals? It's not always the same for all molecules. It's determined using math, and so we're just skimming the surface of this topic. What we need to understand is that B2, C2, and N2 have a different order than O2, F2, and E2. The typical energy orbiting is typical molecular orbital energy ordering is this. The bonding orbitals are lower in energy than the anti-bonding. And it's symmetrical. We've got the sigma is the lowest and the highest. The anti-bonding is the highest energy. The pi bonding orbital is lower and the anti-bonding is higher. So sigma, pi, pi, sigma. That's what we consider normal. So this would be drawing that normal order. So you've got 3 p orbitals and 3 p orbitals. When those combine to form molecular orbitals, we need to end up with 6. So 2 of these, I'm sorry, this is not the normal order. This is the normal order. Sorry about that. 2 of them will overlap end to end and form sigma orbitals. So this one's lower in energy, this one's higher. The other 2 will overlap side to side and form pi orbitals. So we'll get 2 pi bonding orbitals and 2 anti-bonding orbitals. This is what happens with boron, carbon, and nitrogen. And if you look, the difference is that these 2 lower ones are switched. So the expected order is that the sigma bonding is lower in energy than the pi bonding, but over here it's the pi bonding that's lower than the sigma bonding. The upper 2 are the same. So how do we remember this? Well, be careful now. Boron, carbon, and nitrogen. Be careful now. Those are going to switch the order. So these 2 have been switched in order. Be careful now. And down here we have the 2s orbitals, and they're making a sigma and a sigma star. So that's the same on both. Any questions? Isn't this a fun topic for Monday morning? So why is it not the same? There is an increase in the amount of mixing between the 2s and the 2px orbitals for these smaller atoms, boron, carbon, and nitrogen. And so that causes a switch in the order here. You don't need to understand why, you just need to remember, be careful now, switch those two. Okay, so let's look at the rest of the period 2 diatomic molecules. So boron, carbon, nitrogen, oxygen, fluorine, and neon. So boron has 3 valence electrons. So then in our diagram, we're going to put in 6 electrons. So 1, 2, 3, 4, 5, 6. Be careful now, we've got the pi bonding orbitals lower in energy than the sigma. So when we calculate the bond order, here we've got bonding orbital here, and these are bonding orbitals. So a total of 4 electrons in the bonding orbitals, and 2 in the anti-bonding. So 4 minus 2 is 2, divided by 2 is 1. This has a bond order of 2. Of 1. Point to a 1 and say 2. That's awesome. This has a bond order of 1. Carbon, 4 electrons from each. And so then we've got 8 to put into the diagram. 2, 4, 6, 8. So now the pi bonding orbitals are full. Calculate the bond order. We've got 2, 4, 6 in bonding orbitals, minus 2 in anti-bonding orbitals. So that's 4 divided by 2. This has a bond order of 2. Now we said earlier that as the bond order gets larger, the bond gets stronger. And we can measure that as a bond energy or as a bond length. A higher bond energy is stronger. A stronger bond is closer together. The bond length is shorter. So here we see from boron to carbon, the bond energy increasing from 290 kilojoules per mole to 620 kilojoules per mole. And the bond length is decreasing from 159 picometers to 131 picometers. For nitrogen, we're adding 2 more electrons in there. So those are going to go into this sigma bonding orbital. And then when we calculate bond order, we end up with a bond order of 3. When we get to oxygen, the ordering of these molecular orbitals is different. And so now it's sigma first and then pi. So oxygen has 6 valence electrons, so then we've got 12 in our diagram. 2, 4, 6, 8, 10, 11, 12. So we calculate the bond order. Now, we were seeing a trend here that bond order was going up. Now it starts going back down. Because as we're going across here, now we're beginning to add electrons into the anti-bonding orbitals. So oxygen has a bond order of 2. And comparing nitrogen and oxygen, we see lower bond order, lower bond energy, and longer bond length. Fluorine adds 2 more electrons, so those go into pi star, anti-bonding orbital, and its bond order drops. Then we get to neon, where all of these are going to be full, and we're going to get a bond order of 0. There's no bond energy or bond length listed there because this bond doesn't form. Can't measure it. Any questions? Let's watch the long version. So this is looking at paramagnetism.
So we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. Liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled Dewar. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet. Then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
So he's running oxygen gas through those coils, which causes it to condense, and this is liquid oxygen coming out here. It's very cold. Looks like water, right? It's just going straight through. Now the oxygen. You see that? It's sticking. It's staying. It's trapped between the two magnets. Is that crazy or what? It's cool. In fact, it's incredibly cool. It's extremely cold. So what looks like steam here is actually, we see the cold air falling, and it's causing moisture in the air to condense, and so that's actually water vapor condensing, and that's why we can see it. It's basically fog. And that liquid oxygen's boiling away and will be gone. Poof. So the question is, why? Why does oxygen stick in that magnetic field and nitrogen not? Remember we talked about paramagnetic and diamagnetic, and how paramagnetic means that there are unpaired electrons, and so that atom will be attracted to a magnetic field, and a diamagnetic, where all the electrons are paired up, will actually be slightly repelled by a magnetic field. Something. What do you want me to do, computer? There. So we know from experiment, we just watched the video, and of course everything you see on YouTube is true, right? Yeah. We know from experiment that oxygen is paramagnetic. Paramagnetic behavior is a result of unpaired electrons. So if we look at the Lewis model, here's a Lewis model representation of an oxygen molecule. Do you see any unpaired electrons? No, there aren't any. Here's the valence bond model for oxygen. You've got lone pairs on the oxygens, and then you've got a pi bond and a sigma bond. There are no lone pairs. I'm sorry, there are no single electrons, unpaired electrons. So both of these models fail to predict that O2 is paramagnetic. But here's the molecular orbital diagram for oxygen. And what do we see right here? 2 unpaired electrons. If you look at the orbital diagram for nitrogen, there are no unpaired electrons. That's why nitrogen goes straight through the magnet and oxygen does not. Any questions? Okay, let's do this practice problem. Draw an MO diagram and determine the bond order for the N2 plus ion. Do you expect the bond to be stronger or weaker than in the nitrogen molecule? And is this ion diamagnetic or paramagnetic? Okay, so we've got 2s orbitals and 2p orbitals for nitrogen. And then these are going to combine. So the 2s orbitals are going to make a bonding orbital and an anti-bonding orbital. So this is sigma star 2s, and this is sigma 2s. And then those p orbitals are going to overlap. Are we going to use the expected order or the odd, strange order? The strange one. Be careful now, N for nitrogen. So this one does not what we expect. What we expect is that sigma would be lowest and pi would be next. So here we're going to have 2 pi bonding orbitals and then a sigma and then the 2 pi anti-bonding orbitals and a sigma anti-bonding. And these come from these p orbitals. So this is, this is a sigma star 2p. This is pi star 2p. This is sigma 2p, and this is pi 2p. So an N2 plus ion. So we'll look at nitrogen here and N plus over there. It doesn't really matter which one you call the plus. So how many valence electrons does nitrogen have? 5. So we put them in here 1, 2, 3, 4, 5. And over here, an N plus ion would have 4 because it's lost an electron. So 1, 2, 3, 4. So we have a total of 5 plus 4, 9 electrons. Right? So before we fill in the molecular orbitals, could you have 9 electrons that are all paired? No, it's an odd number, right? So there we go. It's going to be paramagnetic, but we still need to do this. So we're going to put 9 electrons in here. So 1, 2, 3, 4, 5, 6. Those are degenerate orbitals. I'm going to fill them singly first before I pair them up. 7, 8, 9. So then we're asked to find whether this bond is stronger or weaker than N2. The bond order for N2 was 3. So the bond order for N2 plus, how many electrons in bonding orbitals?
7.
7. We've got 7 in bonding orbitals. And how many in antibonding? 2. So 7 minus 2 divided by 2. So that's 5 over 2, which is 2.5. Bond order 2.5, bond order 3. Is N2 plus a stronger bond or a weaker bond? Weaker, because its bond order is less. So this is weaker than the N2 molecule. Diamagnetic or paramagnetic? Paramagnetic, because there's one unpaired electron. N2 is diamagnetic, they're all paired up. If you look at the number of electrons and it's an even number, that does not necessarily mean that it's diamagnetic, but it means that it could be. If it's an odd number of electrons, it has to be paramagnetic. Any questions? What if we have heteronuclear diatomic molecules? So the two atoms now are not the same element. Let's look at no. So we've got oxygen, we've got nitrogen. Oxygen is more electronegative than the nitrogen, and so that means its atomic orbitals are going to be lower in energy. So in this diagram here, we see that the nitrogen atomic orbitals are a little higher in energy than the oxygen ones over here. And that's because oxygen is more electronegative. So the low energy atomic orbital contributes more to the bonding orbital, and the higher energy atomic orbital contributes more to the antibonding. So nitrogen with 5, oxygen with 6 electrons. We got 2, 4, 6, 8, 10, 11. Any questions? What about hydrogen and fluorine? So I do not expect you to be able to draw these heteronuclear diagrams. I'm just telling you about them so that you have an idea of some of the things that can happen. So fluorine is the most electronegative element. It's so electronegative that its 2p orbitals are lower in energy than hydrogen's 1s orbital. So hydrogen's 1s orbital is going to overlap with the xp orbital and form a sigma and a sigma star, a bonding and an antibonding. Hydrogen only has this one atomic orbital that it can use, and so we just get a pair of molecular orbitals. What happens to the other 2 p orbitals? Nothing. They're just going to sit there. So these are not antibonding or bonding. They're just non-bonding. They're neutral. So they're just going to sit there. So we've got 7 electrons, although we're not showing the 2s here. So we're looking at 5 electrons from the fluorine and 1 from the hydrogen, and we stick these together, and they'll end up like this. Use molecular orbital theory to determine the bond order of the FO minus ion. What would the name of that ion be? Chlorate is ClO3 minus. So fluorate would be FO3 minus. So this is 2 fewer oxygens, so this would be hypofluorite ion. We can use that pattern to name things even if those things don't actually exist. We can use molecular orbital theory to predict whether this exists or not. So without any outside information, we know that fluorine is more electronegative than oxygen, and so those orbitals would be a little lower in energy, but we don't have to worry about crazy mix-ups like with hydrogen and fluorine. So we're going to look at 2s and 2p. So this will be our fluorine, and we'll put our oxygen over here. Put the oxygen a little higher in energy because it's not as electronegative. So this is our oxygen. Neither of these is, be careful now, boron, carbon, or nitrogen. So this will be the regular ordering. So we're going to get sigma star 2s and sigma 2s from the overlap of the 2s orbitals. And then we're going to get the expected order here. I didn't leave myself much room. Where we got sigma star 2p. This is pi star 2p. Pi 2p and sigma 2p. The reason you want to label these is so that when you look at the bond order, you have identified which ones are bonding and which ones are anti-bonding.
Is the bond sigma 2s?
Yes, that should be an S. Thank you. So we've got sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, sigma star 2p. Isn't this fun? You can say no. We have to make this a negative ion, which means we're adding an electron. We'll end up with the same diagram regardless, but which of these, fluorine or nitrogen, would more like the extra electron? The fluorine, because fluorine's more electronegative, so we're going to give the extra electron to fluorine. Okay, so that means that fluorine has 8, right? 8 valence electrons. So all of these boxes will be full. And oxygen has how many valence electrons? 6. So 1, 2, 3, 4, 5, 6. So we have 6 from the oxygen, 8 from the fluoride. That's 14. So then we'll fill in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we're supposed to identify the bond order. So we're going to look at how many electrons in bonding orbitals. So this is bonding, so that's 2, 4, 6, 8. So 8 in the bonding orbitals. And then anti-bonding orbitals, we got 2, 4, 6. So 8 minus 6 is 2, divided by 2 is 1. Should this ion exist? Yeah, it should. Because when it comes together, the fluoride and the oxygen, that will lower the energy. Is this diamagnetic or paramagnetic? Diamagnetic. Because all of the electrons come in pairs, in twos. They all come in twos. Diamagnetic. Any questions? Well, let's look at some polyatomic molecules, so more than 2 atoms. We looked at ozone when we talked about Lewis theory and valence bond theory. And here's the Lewis structure for ozone, not real satisfactory. We draw 2 resonance structures. Experimentally, we can tell that in ozone, the oxygen bonds are the same. And so here we're saying, well, it's between this one and this one. It's a hybrid of those 2. here's the valence bond model, and here we have to choose to put the double bond between these two oxygens or between the other two oxygens. Also does not explain why or how ozone can have two equivalent bonds. This would be an illustration of a molecular orbital diagram. Well, this is an illustration of an ozone molecule using molecular orbital theory. Let's put it that way. We're not going to draw any diagrams for 3, so that's something to be thankful for. But what's going to happen here is that the pi molecular orbitals are going to form from a combination of the p orbitals on each of these oxygens. And so they will combine and form a delocalized molecular orbital. It's going over the entire molecule. So this would be the pi bond in addition to the sigma bonds that are happening between each of the oxygens. And this is so here we can illustrate how this could be a 1.5 bond, because that second bond is spread out over the whole molecule. Any questions? So benzene is a compound that's very important in organic chemistry. It's a 6-membered carbon ring, and in Lewis theory we represent this as 2 resonance structures. We have alternating double and single bonds around the ring. But we know from experiment that all of those bonds are actually identical. So Lewis theory doesn't describe this. Molecular orbital theory can handle it. So the pi bond, so each of these in valence bond theory would be a sigma bond and a pi bond, and then next door we just have a sigma bond, and then sigma and pi, sigma, sigma and pi, sigma. Molecular orbital theory says, well, those pi bonds are actually spread out over the entire molecule. So we end up with 6 identical carbon-carbon bonds, and they are intermediate in strength between a double and a single bond. This resonance stabilization, this makes this molecule very stable compared to something that maybe had 1 double bond or no double bonds. And this idea of understanding how these resonance things could happen is why we have to talk about molecular orbital theory at all. It's just so we can understand that what's actually happening is those pi bonds are spread out, they're shared by all the atoms in the molecule. When you have that group sharing, it gives it an increased stability.